Hello children, welcome to Deeksha Online. This is part 2 of concept discussion of mechanical properties of solids and fluids under crash course program. In the first part we had discussed mechanical properties of solids, surface tension and viscosity. We will take up the discussion of the idea of fluid mechanics, that is generally known as hydrostatics and hydrodynamics. First we will take up hydrostatics. We will look at the properties of fluids at rest. Later we will take up hydrodynamics, properties of fluids in motion. So first of all, the idea of hydrostatics. In this, we will discuss the properties of fluids at rest. Some of the basic properties of fluids are like this. Number one, the basic idea of density. You know that density is nothing but mass per unit volume. And this is applicable both for liquids and gases, in general fluids. It's a scalar quantity and no direction is associated with this quantity. Now, density is defined as mass of the object divided by volume of the object, as you can see. For a solid object, that means an object which is not hollow from inside, for a solid, completely solid object, density of the object, or say density of the body, is equal to density of the material from which it is made of. Density of the object and density of the material are equal to each other. While for a hollow object, density of the object or density of the body is generally less than density of the material from which it is made of. This is because volume of the object, that is body, is greater than the volume of the material from which it is made of. Simple idea. Suppose I consider the liquids which are mixed with each other. When two immiscible liquids are mixed, then remember the denser liquid is at the bottom while the less denser is at the top. Bottom portion is occupied by the denser liquid. One of the important terminologies which we use here is the idea of relative density or specific gravity. Relative density is represented by RD, specific gravity. This is nothing but density of the object or density of the body divided by density of water. This is also known as specific gravity. Suppose I consider two immiscible liquids, and if I consider liquids which are mixed with each other, not immiscible, let us consider liquids which can be mixed. So, density of the mixture can be understood like this. Suppose we consider two liquids of masses m1 and m2 and their densities are ρ1 and ρ2 respectively. Then the density of the mixture is given by m1 plus m2 divided by m1 by ρ1 plus m2 divided by ρ2, or this can be represented like this: sigma m divided by sigma m by rho, of course from 1 to n. So, I can write mi, rho I, mi, and this is from 1 to n. So, if masses and densities are given, the density of the mixture can be calculated like this. Suppose two liquids of volumes V1 and V2 whose densities ρ1 and ρ2 are mixed, then the density of this mixture is given by ρ1 V1 plus ρ2 V2 divided by V1 plus V2, or this can be written like this: sigma rho I Vi divided by sigma Vi from 1 to n. That is how you find out the density of the mixture of liquids when masses are given or volumes are given. Suppose we consider the variation of density with pressure. Variation of density with pressure. You know that we can write rho is equal to m by v and rho naught is equal to m by v naught. So if I take the ratio, rho divided by rho naught is equal to, what is it, v naught divided by v. But we know that by definition of bulk modulus P is given by minus v naught delta P divided by delta V. That means V is equal to V naught into 1 minus delta P divided by B. So volume variation with respect to pressure is given by this equation. This can be simplified further. We can write rho by rho naught is equal to V naught divided by V, 1 minus delta P by B to the power minus 1, which is nothing but 1 plus delta P divided by, of course this term remains like this, 1 plus delta P divided by B, or we can write rho is equal to rho naught into 1 plus delta P divided by B. So density as a function of pressure can be represented like this. So the density varies with pressure as given by this equation. Variation of density with respect to temperature. Here, you know that rho by rho naught can be written as V naught divided by V naught divided by. Volume changes as given by this equation, V naught into 1 plus gamma delta theta, or rho is given by rho naught divided by 1 plus gamma delta theta. And for small change in temperature, we can write it as rho naught into 1 minus gamma delta theta. So over small variation of temperature, the density can be varied, or density variation can be represented by this equation. The second important property is pressure. You know, pressure at a given point can be defined by this equation. Suppose I consider small force over small area delta S or delta A, then we can write this as limit of delta F by delta S, or this can be written as dF divided by ds, or many a times it is also written as dF divided by dA. So pressure is given by dF divided by ds or dF divided by dA, or many a times the average pressure is written as force per unit area. Here are a couple of important points. Let us consider a liquid and atmospheric pressure is P naught, the exposed part is at pressure P naught. Consider a point which is at a depth h, the density of the liquid being rho. Then the pressure at this depth is given by P is equal to P naught plus rho g h. P naught is the atmospheric pressure and P minus P naught, which is rho g h, is given by, or this is known as gauge pressure. Gauge pressure, which is rho g h. P minus P naught, that is the excess pressure over the atmosphere, is known as gauge pressure. Remember, Even though the pressure is produced by a force that has directional properties and is a vector, the pressure itself is a scalar. And there is no question of direction associated with pressure. It is unique and there is no question of specification of that one. And remember, this pressure acts equally in all the possible directions. That means if a pressure measuring device is at a given point in a fluid, whatever may be its orientation, the pressure measured is same. Pressure always acts normal to the boundaries of the fluid. Remember, pressure is always normal to the boundaries of a fluid. Remember, a very simple concept but quite useful. We also know that according to suppose I consider a liquid which is static. Let us consider a couple of points which are at the same depth. This is H, this is H, this is H, etc. The pressure at all these points, suppose I call these points as X, Y, Z, pressure at X is equal to pressure at Y, which is equal to pressure at Z. Or if you consider, say, connected fluids. If you consider connected fluids, or say connected liquid columns, then the pressure at different pressure inside different liquid columns at a given point are same. For example, if I consider this point, the pressure here, the pressure here are all same. The pressures are all same regardless of the type of the liquid which is present. So remember, as far as the static fluid which is open to the atmosphere is concerned, pressure at A, pressure at B and pressure at C are all equal to each other. So remember this, in the case of connected fluids exposed to atmosphere, at rest the pressure is same at all the points. And you know that this is known as Pascal's law. And remember, it doesn't matter what is the shape of this container, regardless of the container shape, it's the same thing. This Pascal's law can also be represented in a slightly different way. It tells us that if an external pressure is applied in an enclosed fluid, it is transmitted undiminished to every position of the fluid and to the walls of the container as well. So this is what is known as Pascal's law, another version of Pascal's law. One of the very important applications of this fluid is the idea of what is known as buoyancy or say upthrust. Suppose I consider a liquid and if we immerse an object, for example, this is the object immersed. The liquid which is displaced by this object exerts an upward force, and this is what is called as upthrust or buoyant force. This is known as buoyant force. And this is understood in terms of what is known as Archimedes' principle. According to Archimedes' principle, when an object is immersed partly or completely in a liquid, the upthrust or the buoyant force is equal to the weight of the liquid displaced. Weight of the liquid displaced. This is what is known as Archimedes principle. Very simple principle. The magnitude of the buoyant force is equal to weight of the liquid displaced. That is, upthrust is equal to weight of the liquid displaced by the object. And remember, this is applicable both for partly submerged objects or objects which are completely submerged, or an object which is submerged partially in two liquids. For example, this is one liquid, assume, and this is another liquid. Let's assume that there are two liquids and I am representing them like this. Now, if you consider an object which is partly immersed in these two, then there is an upthrust exerted by liquid 1 and liquid 2 respectively. So, the object is under the mercy of both the upthrust exerted by this one, upthrust exerted by the second one. Suppose we consider a couple of applications. Let's assume that there is a container and now we have immersed, we have submerged forcefully an object. That means I am holding this object. What are all the forces exerted? Its weight, I will call it as mg, and the upthrust which is in the upward direction, I will call it as wu. So these are the two forces apart from the force holding the object. So if I release this object, at the instant of release, these are the two forces acting on the object. Now, if mg is greater than upthrust, that means if the weight of the object is greater than the upthrust, then the object sinks. It sinks to the bottom till another force, which is in the form of normal reaction, is available. So it sinks to the bottom, and upon sinking the bottom, it gets one more additional force, which is normal reaction, and thus in addition to upthrust, that normal reaction can keep the object in equilibrium. Suppose mg is equal to upthrust, that means its weight is equal to upthrust, then the object is already in equilibrium and it remains submerged or say immersed in that position. It doesn't move up or it doesn't move down. If the weight is less than the upthrust, what happens? That means weight is less than the upthrust. What happens now? You may notice that there is a net upward force on the object and therefore it rises until it is partially submerged. It is partially immersed or say partially submerged. So if I hold something submerged in an object or say liquid and release it, these are the three possibilities. If the weight is greater, then the object sinks. If the weight is equal to upthrust, then there is no change, it remains suspended inside the liquid. And if the weight is less than the upthrust, the object starts rising up until it is partially out of the liquid and it gets an additional, or rather it starts floating partially submerged. So this is how you analyze the three cases of the object submerged inside the liquid. Some important applications are like this. Suppose I consider this interpretation in terms of density. The object's density is rho, it is solid, assume that it is solid from inside, completely solid, there is no cavity or there is no say vacant space, and the density of the liquid is sigma. Now, if the density rho is greater than sigma, then the object sinks. If rho is equal to sigma, it remains submerged. And if the density rho is less than density of the liquid, it starts rising, it rises and starts floating partially submerged. So these are the three important cases to be kept in mind. There are some important applications of Archimedes' principle. Let's see what are all those. Applications of Archimedes' principle. Number 1, finding relative density of a solid or an object. You know, relative density is given by density of the object, density of the body, divided by density of water. So I am going to write this as weight of body divided by weight of equal volume of water. So further simplification, weight of body divided by weight of equal volume of water is nothing but upthrust. Weight of body, upthrust is nothing but loss in weight of weight in water. So how do I write this? Weight is W naught divided by W naught minus weight in water. Loss of weight in water is nothing but its actual weight minus its weight measured in water. So relative density can be calculated simply by measuring its weight first in air, and we can find out what is its weight in liquid and then taking the ratio. So relative density of the solid can be calculated like this. Second, relative density of a liquid. Relative density of a liquid can be represented like this. You know, the upthrust can be represented. So it's suppose I write it like this. Loss in weight of of an object in water is A, and let's consider, I'll write it like this. Loss in weight of the body in water is A. Loss of weight in liquid is B. So what is that? So then the upthrust is equal to V sigma of water into G, and upthrust, this is in water, this is in liquid, V density of liquid into G. This is equal to A, this is equal to B, this is equal to A. So I am going to take the ratio. If I take the ratio, what do I get? Sigma L divided by sigma of water is equal to B by A. But you know, B is the loss in water, so I am going to write it as W naught minus weight in liquid, W naught minus weight in water. So the relative density, that is sigma L divided by sigma of water, that is the relative density, is simply its weight in air, actual weight, minus weight in liquid, its weight minus weight in water. So, relative density of the liquid can be found out using this expression. Third, to determine volume of a cavity, to determine the volume of a cavity in a body. Suppose the weight of the body in air is say W naught, and the weight of the object in water is W, represented like this. So, I can write volume is equal to loss in weight divided by sigma into G. That is nothing but the upthrust equation. That is nothing but W naught minus W of water divided by sigma into G. While the volume of material of the body is equal to V naught, which is nothing but mass of the body in air divided by density of the material. So, we can calculate this. Therefore, volume of the cavity is equal to V. This is nothing but V volume, V minus V naught. So, we can subtract one from the other and we can find out like this. So, we can find out the volume of the cavity using this concept. And one more, determination of impurity. Determination of impurity in a given metal. Suppose a solid of mass m contains impurity, assume it to be Y, and its density is rho 1. What is rho 1? This is of density rho 1. Impurities of density, say, let's assume that density of the pure material is density rho m. I'll call it as rho L. Then we can write volume of impurity, V1 is Y divided by rho 1. Volume of pure metal should be Vm is equal to, I'll call it as Vm, which is m minus Y divided by rho m. So, total volume V is equal to V1 plus Vm, that's the total volume of the body, which is Y by rho L plus m minus Y divided rho 1, that is divided by rho m. But I'll call this as equation 1. But we can also represent the volume like this. Volume is equal to W naught minus its weight in water divided by sigma, that is density of water. So, this is your equation number 2. Now, we can equate 1 and 2, and if I equate 1 and 2, we can calculate the value of Y. So, it's basically a question of substitution now. So, the extent of impurity of a material present in a pure metal can also be calculated like this. So, these are some important application as far as Archimedes principle is concerned. Suppose I consider the case of equilibrium of an object in a liquid or inside a fluid. How do we do this? Suppose I consider, say, something like this. A liquid is present here and a floating body slightly tilted from equilibrium position. For example, there is an object. Let's assume that this is a cube which is present like this, and I rotate it slightly and release. What happens? Then the center of buoyancy shifts to a new position. And then, for example, here the center of buoyancy shifts to a new position. It was here, and then upon rotating, the center of buoyancy shifts to a new position like this. And the vertical line passing through the new center of buoyancy and the initial vertical line meet at a particular point called metacenter. This is what is known as metacenter. Now, if the metacenter is above the center of gravity, then the upthrust tends to bring the body back to its original position. That means for rotational equilibrium, remember, the metacenter must be above the center of gravity. Otherwise, what happens is that the torque will pull it down and it gets shifted and the object topples. That means if the metacenter goes below the center of gravity, the couple formed due to the weight and the upthrust tend to topple the given object. So remember how to represent this idea, that is the idea of the rotational equilibrium of a given object. Rotational equilibrium is possible only when this condition is met. So these are some key ideas as far as the liquids at rest are considered. The key ideas are very simple. Learn the basic ideas of Archimedes principle and the laws of flotation. Let us now consider the ideas of hydrodynamics, that means fluids in motion. Here we consider a fluid which is in motion. The two key ideas in this chapter are, or say in this concept are, mass conservation principle and energy conservation principle. These are the two key ideas as far as this chapter is concerned. Let us consider, say, a pipe of varying cross section like this. Let's assume that A is this cross sectional area. The speed of the liquid which is entering here is V, or say we will call it as A1 and V1. Liquid comes out from the other cross section at a speed V2, cross sectional area being A2. And the same thing happens everywhere also. If I consider this cross section as A, and the fluid which is coming out here is coming out at a speed V, then the density of the liquid rho, as you can notice, remains constant everywhere, which means that the volume of the fluid flowing per unit time should remain constant. So if I consider a small extent of liquid which is flowing here, whose length is, say, some delta x, and a liquid takes time delta t to cross this one. So clearly, volume of the fluid, mass of the fluid flown per unit time should remain constant. So I'll write dm divided by dt is equal to constant. What is that dm by dt? d by dt of mass. Mass, you know, is density into volume. So I'm going to write it as rho a into x is equal to constant. or we will write as rho into A into dx divided by dt is equal to constant. Or we can write rho A dx by dt can be calculated over a length. I can write as delta x by delta t. Or I can write rho A into v is equal to constant, as this delta x by delta t is nothing but velocity. Or I can write rho 1 A1 V1 is equal to rho 2 A2 V2 is equal to rho 3 A3 V3 etc. is equal to constant. Now, if I assume that the density of the liquid remains constant everywhere, we can say rho 1 is equal to rho 2 is equal to rho 3 etc. and that is rho, or we can simply write AV is equal to constant, or A1 V1 is equal to A2 V2 in the previous diagram that is shown. So AV is equal to constant, and this is what is called as principle of equation of continuity, according to which the total volume of the total mass of the liquid crossing a given pipe is constant with respect to time. But if you ask what does that AV give you, observe it carefully, A into delta x divided by delta t. But you know, A into delta x is nothing but volume. So this is nothing but delta V by delta t is equal to constant. It tells you volume flow rate. So this is nothing but volume flow rate. So equation of continuity can be interpreted as mass per unit time is constant or volume per unit time is constant. Any of these two representations is perfectly fine. If you are talking of constant density, then volume flow rate remains constant is a better description of the given situation. The second is energy conservation, given in the form of Bernoulli's theorem. According to which, in the case of a steady flow of incompressible and non-viscous fluid through a tube of non-uniform cross-section, the sum of pressure energy, potential energy and kinetic energy per unit volume is constant. For example, you can consider a liquid flown in a pipe. Now, I can say this is of cross-sectional area A1. Liquid enters this at a speed V1 and this is at a height H1 and the pressure here is P1. Likewise, A2 and V2 are the quantities here, P2 is the pressure over here and H2 is the height of this. So here what it tells is pressure energy plus kinetic energy plus potential energy is constant. Obviously, in the case of an incompressible fluid which is not undergoing any rotation and there is no question of viscosity, then PV plus half mv square plus mgh is constant. Now, if I divide by V throughout, what do I get? If I divide by V throughout, then P plus half rho V square plus rho GH is equal to constant. This is what is known as Bernoulli's theorem. Many times this is written as P1 plus half rho 1 V1 square plus rho 1 GH1 is equal to P2 plus half rho 2 V2 square plus rho 2 GH2. This is constant. If the liquid is flowing at the same horizontal level, then even rho GH becomes constant. That means if H1 is equal to H2, we have P1 plus half rho 1 V1 square is equal to P2 plus half rho 2 V2 square. That means we can also write it like this: P plus half rho V square is equal to constant. That's right. So we notice that if the velocity is large, pressure is small. And if the pressure is large, velocity is small. So when a fluid flows from broader to narrower pipe, the velocity increases and thus the pressure decreases. So remember, this is a key concept which should be kept in mind. So let me repeat it. When a fluid flows from broader to narrower pipe, wider to narrower pipe, velocity decreases. Velocity decreases from continuity equation. If the velocity decreases, then the pressure decreases, right? Velocity increases and the pressure decreases. The various applications of Bernoulli's theorem, for example, whenever in a high-speed storm, the roofs of the houses detach themselves, right? They blow off. This is because pressure below the roof is atmospheric pressure, while above it is very high. So low pressure because velocity is high and the pressure is less, and thus due to this there is an upward pressure exerted and thus the roof is lifted up and it goes off. Or if you consider two closely parallel moving boats or buses or trains, then what happens is that between them the pressure decreases, right? Because the velocity is very high and thus the pressure decreases. And as the pressures decrease, there is a pressure difference which is created towards each other and they try to push, or rather they are attracted or pulled towards each other. So there are some applications of Bernoulli's theorem in daily life. One of the very important applications is what is called as speed of efflux. Speed of efflux. So what is that speed of efflux? We take a container and let's assume that liquid of density rho is filled here and a hole is made at a depth h below the free surface. There is a hole which is made at a depth h below the free surface. Then the liquid oozes out, it comes out, and the speed with which it comes out is called as speed of efflux. And the speed of efflux is given by square root of 2gh. Speed of efflux is given by square root of 2gh. So now, as you can notice, if I consider couple of orifices or say holes, for example, this hole is at a depth h1, another is at a depth h2, etc. Then this liquid comes slowly, this liquid is faster, etc. So V1 is equal to root of 2gh1, V2 is equal to root of 2gh2, etc. Now as h2 is greater than h1, the speed with which it comes out is more than the speed with which the top fluid comes. Suppose this liquid is at a hole is at a depth h and the liquid column is of depth h. That means this is h minus h. Then we can find out the time required by this, the time required by the liquid to reach the base level can be found out. And the range of the liquid flowing from the orifice also can be found out. Suppose I consider the hole is at the bottom of the tank. Let us assume that in one more case, the hole is at the bottom of the tank and the tank is of depth h. Then the time, suppose this is of area A naught, the free surface is of area A. Then the time required for the liquid to come to the bottom of the tank, that means the time required to empty the tank, is given by A divided by A naught square root of 2h divided by g. So this is the total time required by the liquid to fall from a height h, or say height 0 to bottom h. So this is how you find the time required to empty the container. We can also find out the time required by the liquid, this is h, the time required by the liquid to strike this point, the range, etc. As the vertical velocity of the liquid at the orifice is 0, suppose I consider the vertical velocity, vertical velocity is 0 at the beginning, right? And therefore, the time taken by the liquid to reach this level, so the liquid which falls off, strike this level, it is as good as free fall. So the time required by the liquid which is coming out, I repeat, the time required by the liquid which is coming out to reach this bottom level is given by square root of 2 h minus h divided by g, this height being h minus h. So the liquid which is coming out takes this time to reach the ground level. And we can also find out the range. Range is equal to velocity into time taken. Velocity is the speed with which it comes out, and the speed with which it comes out is horizontal, velocity is horizontal, and that is given by square root of 2gh. The time taken is the same both for horizontal and vertical motions, that is 2h minus h divided by g, or you can simplify it further and this becomes 2 root h into h minus h. And this range clearly is maximum when h is equal to h divided by 2. That means if the hole is punched at the midpoint, then the range of the liquid coming out is maximum. This range is same whether the hole is at a depth of h or h minus h. You may notice that the range is same whether the hole is at a depth h or at a depth h minus h. So you may notice that the same equation tells us the same thing. This equation tells us the same thing, because the range is given by 2 root of h into h minus h. Whether this is taken as the depth of the hole from the top or h minus h is taken as the depth of the hole from the top, in both the cases the range remains the same. So it is regardless of this idea. That means whether the hole is punched at a depth of h from top or at a height of h from the bottom does not matter. The range is same in both the cases. So these are some key ideas as far as hydrodynamics is concerned. Remember, it is a pretty simple concept. The two important concepts are mass conservation principle and energy conservation principle. So in both the cases, the conservation principle is put into use, and remember the equations which are quite useful in this chapter. In our next session, we are going to take up numerical problems based on the concepts that we have learned. Thank you very much.